Welcome to the physics video lecture once again. This is Psci 168, video lecture 30. We are talking about solar energy now, and I spent a good amount of time discussing how we measure the solar constant. So very briefly, I'll reiterate that, but let's put the definition down that we had arrived at. So the solar constant, it is 1,340 watts per square meter. Watts per meter squared. So it is a power per area that's referred to as an intensity. And this would be up above the atmosphere on the boundary of outer space where there's nothing to reflect the sunlight away. We can take as a nice round number, especially when we're doing our estimations, we can say down here on Earth at noon we would get about 1,000. Okay? So this is, I'll just write above the atmosphere. So when we want to do our estimates and things, we can just use 1,000. That's a nice round number. Either way, that's quite a bit of energy. Okay? That's quite a bit of power per square meter. And how did we discover this? Well, very carefully we put a solar collector out here with water in it, water and a thermometer, and we just let the sun heat the water. So the sunlight heats the water in there. Maybe the water has black ink in it or something to make it really absorb all the radiation, and there's a certain mass of water in there, and the temperature in the water increases. And what we did was we constructed this expression to be P over T, power over area, and we said that was MC delta temperature over delta time. Okay, so MC delta T is an energy divided by time is a power divided by area. So those were all the ingredients in discovering this, and if you actually graphed the temperature increase as a function, or just, this is what we had last time, just briefly, your temperature as a function of time, and it would go up like that, and then your delta T over delta T, temperature over time, would be the slope of that graph, and you'd put together your experiment with a lot of patience, and then you come up with a number like this. And we know that there is such thing as energy conservation, which means energy can change form. So even though this is thermal energy, we already know we can turn it into work with a heat engine, and we're going to learn that we can turn it into direct electricity with photovoltaic cells. So there's a lot of potential here. Okay. Energy from the sun. And I'll put a couple of points about the energy from the sun. Right, I'll just for a picture again. We had this last time, so it's in your notes. Sunlight, area A, mass M of water. And so, okay. So that's how we get the solar constant. And this is the result that we're going to use. So, applications now. We have, for solar energy, we can just stand out in the sun and get warmed. We can just put water out in the sun and warm it. In other words, solar energy can just be used for direct heat. So direct heat is one application. Another one, if we can collect the heat in a certain way, we can run a heat engine, and I'll detail that in a moment. So collect heat, or collect thermal energy. Let's write collect thermal energy and run a heat engine. If we could do that, then we would be using this and getting work out of it, okay? Because we know that's what the heat engine's for, to get work. A third application is direct conversion of sunlight to electricity. Direct conversion to electricity, by which I mean to electrical power. A fourth application, I'm on a roll here. A fourth application, we have to go back to that solar chimney and remember that the presence of a temperature gradient gives rise to convection currents, which is to say wind. So wind energy is actually a consequence of solar energy. So we're going to actually discuss the wind energy. I'll just write here, temperature differences. And the reason we have temperature differences is that the Earth is not uniformly heated, right? The North Pole, South Pole are colder than the equator. Right there you have a temperature difference that's going to give rise to weather. And then just locally, the hillside will be hotter on one side than the other, and the building will be hotter on one side than the other. Hence, you get convection currents, which is to say you get wind. So wind is a direct consequence of this indirect heating. Temperature differences, i.e. Uneven heating, not indirect, uneven heating gives rise to convection, right? We know that word. Convection currents. And what is that? That's wind. So we can talk about how to harvest wind energy as well. Now, this number there will not be directly in play the way it is in these other examples. There it's in the background, and we'll treat wind separately. But another topic, these applications we could also just call topics, since I'm here listing them all. What we're going to do at some point in this discussion is discover how powerful is the sun itself, right? This is how much reaches Earth, how powerful is the sun, and what does that tell us about the energy production in the sun? So energy production in the sun, and we're going to need some of our astronomical data from earlier in the semester to do that. So that's a really interesting topic. It leads to unexpected places. Okay, direct heat, I'm not going to say any more about. Collecting thermal energy to run a heat engine, that's what we'll do as our next topic. And what those are referred to as are solar thermal power plants. There are a number of these. There's one in Kalinga. There are some out there on the way to Las Vegas. So you're going to find some really interesting images for these, and I'll give you a list of things to look up after I discuss what's going on there. This is called the central tower. I'll just write central tower with heliostats. So these are all, make sure I write it out clearly, heliostats. This is all terminology you can type in when you're looking for images. So what's going on with the central power, the solar thermal power plant in the central tower? Well, there is, I'll start with the heliostats. These heliostats are mirrors that are aimed in such a way, so there's a mirror on a stand. There's a mirror. And when the sun hits the mirror, say the sun is up here, you get a reflection of the light to that central tower. So the central tower here, I'll use black, has a collector, and then it's just a tall steel tower. Okay. There's not just one mirror, there are many of them, but the idea is they reflect the sunlight and it is aimed at the central tower. In fact, as the sun crosses the sky, those heliostats that are reflecting the sunlight, they move in such a way as to keep reflecting it to the central tower there. So they actually have, they're motorized so that they move with the sun. So there's a whole field of these mirrors. In fact, it could be several, as large as several football fields. So I'll put a note here, an entire field of such mirrors. And so there's a field of them. They produce an immense heat right here because they're concentrating all the light that hits an entire football field or greater, maybe a couple acres even, at 1,000 watts per square meter, maybe dozens of acres. These things are really large, and you guys are going to look that up and get some good images for that. Okay, so you produce a lot of heat right here. You have to take that heat into your power plant. So I'm going to do a schematic drawing here. Wish me luck. What this heat collector has, I'll call it the collector, it's filled with a molten salt. And that molten salt is then channeled. Let's see what color I'll use, blue here. It's channeled over to a set of tanks. So what I'm going to do is draw the tanks here first. You're going to recognize our heat engine pretty nicely, and I'll call this the powerhouse. So this is T sub H. It's actually full of molten salt. Salt was up here, gets piped in to this tank there. Okay. Very, very hot because you focus that light from the entire field onto that one small spot. Okay. Then I'm just going to write work here. That's where the heat engine is located, and then the work is done there. This is T sub C. Let's make sure these arrows are right. Arrows back up into the tower. Here it's coming down. Okay. I should have spaced these a little farther apart. Okay, so this is a tank of hot molten salt that goes into the powerhouse, delivers some work via heat engines, and then goes to the colder salt. So you see our schema here with high temperature reservoir, low temperature reservoir, and the engine there. You know, we could even say that we were delivering the QH here, and we're delivering the QC there. This is our old heat engine schema, and the collection of the energy in the high temperature reservoir, the hot molten salt, allows this device to function on a cloudy day, okay, or overnight, because overnight there's no radiation here anymore, but you've collected enough thermal energy to keep running the whole process. So overnight, and then maybe, depending on how much you collect, you could have so many days of cloudy weather. So that's a solar thermal power plant, central tower with heliostats. So you can find very good real imagery and schematic imagery that you're going to want to look up and print out for this. Let me list a couple of names. Yeah, I feel like I could have had a slightly better picture, but I'm just going to write here, recall our heat engine schematic. Because that is what we're looking at right here. That's the idea. And this uses a molten salt as a liquid to go through there. Principally, you could use water, but it would generate a lot of pressure because it would be so hot it would be steam. But in this case, they use a molten salt, and they can actually store the energy. So let me send this up. And I want to send you guys out to find some very nice images of this. And I'll kind of give a list for you. So images, that's our homework for this topic here. There is a power plant of this type that actually uses the heat and not the power generation, uses it to assist in oil recovery, but it's out in Kalinga. You can, in fact, go onto the Google Maps program and just scan over to Kalinga, and if you keep your eyes peeled, you'll actually see this thing from the aerial view. So you can literally do aerial views of these things and get screenshots, as well as other pictures that'll be there available for you. In that case, I believe it's a field that's kind of this shape here, and the tower is right here, and then you have a whole field of heliostats. We talked about the location of the sun, so you put this thing towards the south end of the field, and the sunlight is reflected towards the central tower. So that's one to look up. Another location, it's either California or Nevada out towards Vegas, called Ivan Pa. Don't know what that name means. This is a major operation with several central towers, so it's huge. There was formerly out in Daggett, and Daggett is out also on the way to Las Vegas. There was one called Solar One, That one has actually been disassembled. If you look at it from the aerial view, you can actually see the fields where this one was located. You'll still find images for this. So yeah, we want to see a lot of images of these solar thermal power plants. So in addition to just these images, let's say we also want to see if you can find some of the technical details, namely see if you can locate, I mean there's a ton of information out there, but in particular what we'd like to find out, what are these high and low temperatures in the high and low temperature reservoirs? So let's write, what are the values for TH and TC? I remember for solar one, they were available. See what's going on out there, okay, in terms of these things here. Solar thermal power plants. That's our major project. Let me consult the clock. Okay. So yeah, we want images for these operations here. I'm making a list here. In particular, we also want images of heliostats. For one of these, what I really prefer for you to do is zoom in on it and from, say, the Google Maps program, estimate the area, estimate the area of the mirrors, and you can then get an estimate of the actual power that can be derived. So that's something you want to think about when you're generating these things. So this is all homework, how to determine or how about, let's be a little more cautious here, how to estimate power output. That's a question mark. So let's talk about that. So suppose you were to look at one of these things and you just based on what you can find from looking at the map from the satellite view, can you estimate the power output? Of course, if they have a website, they may tell you what the power output is, but we'd really like to understand how much power is there based on our own knowledge. So let's do that. How to estimate the power output. I'll leave this picture up. It's nice. It could be better, but there we go. So we want to estimate the power output. Remember, this is a heat engine. This is a heat engine, and the energy source is sunlight, but it's being gathered as thermal energy. So I'm even going to draw a small version of our heat engine just to remind you. QC into TC. Yeah, right now this is a big tank full of molten salt. Energy came from the sun, and then we're sending this here into the actual heat engine power plant. And that includes the lower temperature storage, which, by the way, this is not cold, but it's lower than the high temperature storage. So remember, we had efficiency is equal to work over QH. So we can say the work is the efficiency times QH. Fine. This would be the power output. in joules, and if you have, joules per second, that would be the watts, okay? So work over time, QH over time. So we'll stick with this right here. Now what about the efficiency? Efficiency is 1 minus TC over TH. So if you have those informations, TC and TH, in Kelvin, and if they gave you in Fahrenheit, you would have to do a couple conversions to Kelvin. In Kelvin, then you'd have that efficiency. So then you would need this QH, okay? But since it's a power, this would be work over time, and this would be QH over time. Okay, we'll get to that last. So the question then is, how do you get this QH? Actually, we won't get to it last. Let me make some room here. I'm going to leave that picture up. Let's modify that formula here. So we would have from star right there. So from equation star, we would have the power would be that efficiency times delta QH over delta T, because the W over T, or delta T, that's the power. So it's efficiency delta QH over delta T. Okay. And this, of course, is a power as well. And this would be estimated using the solar energy expression, where delta QH over delta T, which is a power, would be equal to I, solar constant, times A, which is area. I times A. So that we'll just call 1,000 watts per meter squared. How many square meters do we have? So this would be the solar constant. And this would be area. Area of solar collectors. Which in the case of these things is the mirrors. So that's how it would actually be done. If we knew these temperatures, we'd get this maximum possible efficiency, so that would be a number less than 1. And then if we knew the area, we'd multiply it by the solar constant. Now that's a theoretical maximum. In reality, you're going to be striving for that and getting some amount that's less. For example, you may have to average all this over the course of a day. You don't have full sunlight each day. That type of thing. Okay, good. I'm going to leave it at that today. I want you guys to go out and look these things up and try to get some good images, first of all, and then even try to get the temperature information if you can. These kind of operations, they have a website. They gladly tell you how much power they deliver. But what we want to do is understand it in terms of the area of the solar collectors. Good, we'll leave it at that, and see you guys next time.